Okay, so let me just make some summary so that we can record all the thing. So when we zoom in the paraboloid, we see that the paraboloid is coincide the tangent plane at this point. So at nearby this point, we see that the tangent plane is actually getting a similar property with the surface of paraboloid, and we can take this as our approach to approximate, or we can say that's linear approximation, and we call that the tangent plane as linearization. Okay, so approximation or linear approximation will be equal to, we can write the function x, y. We can write this is our approximation. Okay. So for instance, if we take the point 1.1 and 0.95 for x and y, we can check the approximation is equal to 4.11 plus 2, 0.95 minus 3. This equal to 3.3. Now if we take this into our functions, this will be giving us similar results, almost similar. We see that we have some 0.025 difference, and depends on the tolerance of the error. I think this is very close. Right? I think very close. And let me write in the side here the conclusions. First is equation of tangent plane. This is z equal fab partial x ab x minus a plus partial y ab y minus b. Okay, that's the tangent plane. And the linear function, the linearization, basically this is the all is the same thing. Okay. Basically all the same structure. There's a slight difference. This is we called linear approximation. Linear approximations of tangent plane not tangent plane, sorry. The linear approximation of the function at a b. And how we are going to use this is precisely similar to the linear approximation in calculus 1. Okay. So first we need to set up formulations. meaning we set up the tangent plane. That's the first thing. Secondly, depends on the question whether it's just asking the linearizations or it's asking some error or maybe evaluating the value. Then if you want to evaluate the value, then we need to take the point nearby the point that we are going to calculate, and we are going to set up the point that is easy to calculate within the tangent plane. And then by doing that, then we can have a tangent plane. Okay, so linearizations and linear approximation. And by the way, the midterm results, I've checked all. I think, wait a minute. I've checked. Let me check the average. Yeah, the average is 69.2. That's the average. The highest one is 90. The lowest 49. Yeah, 49. Okay, any questions so far from this linear approximation? I think practically speaking, how we are going to use this approximation is basically similar to what we have done in calculus 1. Okay, let's continue. Okay, let's continue. No question. Let's continue a little bit on this linear approximations and the idea on differentials, partial differentials. First, let me go through here. So this is the graph for. Let me write the functions. Let's have a piecewise definition for this function of two variables. Now this is if the point is not at the origin, and this if the point is at the origin. Okay, you can verify that this partial derivative, okay, for this f of xy, it exists at origin. Okay, and in fact, if you check it exists at origin, but this partial x and partial y are not continuous. The linear approximations would be partial xy. This should be approximate 0. Okay, but fxy can be half for path y equal x. So in fact, this function of two variables fxy, they can behave badly even though the partial derivative exists. Now we can rule out this. Okay. We can rule out with the idea of differentiable function of two variables. Now recall we have function of x. Okay. If x changes from a to a plus delta x, we define the delta y as f a plus delta x minus f of a. Okay, if you remember the differentials that we've done in calculus 1. If the function differentiable at a, then we can write this and we introduce to the epsilon, right? The epsilon. This is, I think, in chapter 3 in calculus 1, where epsilon, when the epsilon is getting 0 as the delta x getting 0. Now we consider, instead of one variable, now we consider if we have two variables. Okay, so consider z function of xy, and suppose x changes from a to a plus delta x. Okay, and y change from b to b plus delta y. Now we consider these two changes because it is two variables. Now we can define the difference in z, or the increment of z, as delta z, and this will be equal to f a plus delta x b plus delta y minus f a b. So we set up the increment of z that represent changes in the value of f when the point changes from ab to a plus delta x b plus delta y. And thus from here we can have a good definition. I'll write the definition at the next page. Okay. But you can write notes if you want from here. So as in analogical from calculus 1, that we have the delta y. Okay. So the delta y is depending on x. Now we are saying that z, it depends on x and also y at the same time. So we can define the differentiability of z, or function of two variables. Okay. Now you can write the definition. If z is a function of two variables, then f is differentiable at point AB if delta z delta z can be expressed in the form and then we have epsilon for each changes in x and y. We can also relate this epsilon to error, okay, where epsilon 1 and epsilon 2 are functions of delta x and delta y such that epsilon 1 and epsilon 2, they both going to be 0, or maybe let me write such that epsilon 1 going to 0, epsilon 2 going to 0, as the delta goes to 0. So if you confused on the words here, let me just express in a way that you can imagine. Previously, we see that, or in calculus 1, we see that the linear approximation is good when we approximate nearby the point that we are going to evaluate, right? The more close we are, we will have much more good approximations. And similarly, when we have function of two variables, and when we are going to approximate the surface, the tangent plane, okay, if we want to pick up the point, so the nearby point will be a very good choice, right? Will be a very good choice because it has a good approximation. In other words, from this expression, it's actually saying that the tangent plane approximates the graph or the surface or graph of f well, okay, or good near the point of tangency, or the point that we are evaluating. Why nearby is very good choice? Because when we have near point, then we are going to have this epsilon is getting 0 through the limit concept. Okay. So when we have this 0, then we can have the perfect perfect tangent plane, right? Perfect tangent plane. Now from this part, we are getting a new theorem that says that if partial x and partial y exists near AB, the point of our observation, and continuous at AB, then f is differentiable. Okay, now this is the truly the conclusions. Okay, the implication that is important for you. Okay, so partial x, partial y exists. Okay, in the terms of partial derivatives, and they both continue. They both continuous. How well we know the partial x, partial y continues? We know well from the approximation that we have before. Okay. More clear approximation or good approximation, it seems that it is giving us a good view for its continuity, for the partial derivative. Okay. Because if we see the graph, let me go here before. If we see this graph, if you see this one, it has some problem here, right? We have some problem, and if we are going to take the y equal x path, the curve y equal x here, they are having 1 over 2 in every y equal x, and thus if we take the tangent plane, it will be very difficult to imagine, right? Where does the tangent plane is at the origin, at the 0 0. Is it here or is it below? It's difficult, right? Because the partial derivative for x and y is not continuous. That's the problem. That's the problem. So the way we are seeing this problem is by imagining the approximations. Okay, the approximation. The more we have the where is it? Here. The more we have, the clearer we have here. When we are going to zoom in, become here, become this becoming perfect, and we can say that both tangent, they are exist and continuous, right? Continue means there's nothing that is obstruct or obstacle in between those tangents. Okay, so this is the implication, the theorem. So we need to make sure that partial x and partial y exists near the point of observations and continues. With these two requirements, then we can say the function is differentiable, or the z is differentiable. Okay, any questions? Do you feel confused or not? I hope not. Yeah, I hope not. Any questions so far? Okay. Okay. From this delta z, okay, we are going to use the the definition in differential. Okay, and I think for some parts, I believe in physics there are some formulations that is written using the partials or the differentials, because we have interdependency for variables, like not only one variable but maybe the same time more than one. Okay, multivariables. So we actually define x and y. They are both independent, and the only one that is dependent is only z. Okay, if we look how the equation is in the tangent plane, in the linear approximations. Okay, both actually similar formulations. The difference is how we apply the formula. That will be slightly different. Okay, so for differentials, imagine we have function of two variables as z. So we define dx and dy to be independent. So they can be given any values. Now the dz, also called the total differential, is defined by dz oh sorry, I forgot to write dx, or can write this is in terms of differentials, in which mostly using for to determine the error, or to show how well the approximation is. So the linear approximation we can write in differential notation. So the differentials means the notation is having this d. The structure is similar actually. We can write dz as, if you want to take the delta x as x minus a, we can also write if you want to be more concise on the point AB, then we can write in terms of AB for all the equation. And the notation differentials for linear approximations, we can write FAB plus DZ. So this will be the linear approximation. So whenever we have a value that changes on x and y, then we can simply put into our equation for differential equations, and we put all the numbers, okay, that changes, and we can find what will happen with c, okay, in terms of the changes. Okay. So if we have a functions and we want to find the differential dz. So we need to derive the functions partially. So we might take partial x and then partial y and then put all the information that you have. Or just simply, if you just ask the equations, then just partial x and then just dx, and partial y and dy, and that's your differentials of dz. So if you have more than two, what happened with three variables, it's actually similar. It's actually similar. Maybe you just need to add more variables. So you will have the delta. Okay, you have the delta. So dz will be equal to the, or here if we write dz, we can write as the difference between this function or maybe let me give you the context on the graph. So this is actually how it looks like if we look on the differentials. Okay. So the important thing here is this, okay, this part. You see that it has difference because dz actually refers to the tangent plane that we have, right? From the equations that we discussed before. And if we look on the truth, that the delta z is actually having much more higher. So then, if you're going to approach this AB, you will see that from this gap and goes to here, the gap is getting closer. Okay, it's getting closer, and we prove that in the linear approximations, right? And all the dx and dy, they are independent. Okay, so not our concern. So we concern here is in the z, and this is the tangent plane. Okay, do you still want to write the notes from the previous page or this one? Or it's okay? Okay. Now, how we can actually apply this differential? First, we can apply in a set of approximations. And also optimizations. If you remember optimization in calculus 1, we can also apply similar optimization but in partials. Let me give you the context here. Dimensions of boxes are okay, we have 3 lengths for box. Each measurement is correct within 0.2 centimeters. So we have an error. So use differentials to estimate largest possible error when volume of the box calculated. Okay, I think this is very pretty clear, the objective. So the objective is actually finding error for the volume. Okay, finding error for the volume. So we have the size, we have the error, then we might to check the formulation of the volume first. So the volume, or if you want to look at the question first and then think, you can try first to look at. And it doesn't specifically say which length or which variable that are dependent or independent. So I think they are all independent variable. So if we imagine the length as x, y, and z, for 75 centimeter, 60 centimeter, 40 centimeter, they are all independent. So we need to develop a new function that that can be includes is x, y, z. So we can probably say it as volume as v equal x, y, z. This is our formulation because there is nothing provided in the information, so we just state x, y, z. So this is our formula. Okay, so because this volume is the one that we are going to evaluate its error, the error of the volume, then if we looking back what we have here, this is actually the difference between this is our error, right? So that's how we can see from this picture. So the same thing when we differentiate this, when we partially differentiate, we will see that later we will have some percentage of error if we compare with the real size of this value. So we can compare both value. And this 0.2 will be error for each x, y, z. So we can say that 0.2 centimeter is error for each length. Or we can say that the x is 0.2, dy is 0.2, and dz is 0.2. Okay? I hope this explanation can be understandable. Now, we are going to partially differentiate, or we find the dv. This will be equal to or maybe let's partially differentiate each one. So we find partial x, partial y, and partial z. So partial x, we are just having yz. Partial y, we are having xz. And partial z, we're having xy. And now we can put into our, we can say the differentials. Okay, this is yz dx, right? This is partial x. partial y partial z plus xc dy plus xy dz. So this is our differentials. Now we calculate for dv, we calculate all. So let's say this is xyz. So this is 60, 40, and 0.2. This is 75. Sorry, maybe 75, 40, 0.2 plus 75, 60, 0.2. This will be 2 for 100. This will be 3,000. This will be 4,500. And all will be and multiply with 2, 240, 5, 990 multiplied by 2 is 19, so dV is 1980 centimeter cube. Now the volume itself is 75, 60, 40. This equal to 24. Okay, so the percentage will be dV over V multiplied by 100. So 1980 multiplied with is almost 1.1%. So this will be the error for the volume. Error of volume. Okay. Okay. Any questions? I think very clear, right? It's a simple example. Okay. If there's no questions, I will review a little bit from some examples that we have, and I think I also mentioned last time on the attachment for exercise. And I think since some of you giving feedbacks on the course that we might need more discussion and more about essential question, or maybe perhaps just a regular exercise. So let me just review and see some questions. Some questions. Let me check. Maybe here. Okay. Yeah, probably. Let me check which one. I think. Okay, maybe we start from maybe 38. And maybe 44. And maybe 58. Okay, we start from 38. Y sine inverse xy, and we need to find the partial y at 1 and half, at point 1 and half. Now, if you forget how to derive the inverse, then maybe you can start with deriving from the scratch, from the definition itself. Let me write what we can do for the sine inverse. You can also try by yourself. Okay, I hope you can try to improve. Number 38. So f xy. This is y. Sine inverse xy. Sorry. And we need to find partial y at 1 and half. Now let's start with y equals sine inverse x. If you don't remember how to derive, then we can say x is sine y. Okay, and then we can try to draw in a triangle like this, and say that this is the angle, right? Because the inverse is actually talking about the angle. Now sine y will be x1, right? So this will be 1 minus x squared, like that. Okay. Now we can differentiate this using the implicit. Then we will have 1. Sine become cos y and dy over dx. Now dy over dx is our derivative that we are going to find. So dy over dx, this becomes 1 over cos y. And cos will be, so cos y is equal square root of 1 minus x. So this will be 1 over square root of 1 minus x squared. This is if sometimes happen and you maybe forget what is the formulations for sine inverse. This is what we can do. Okay. Not really long to prove that, to prove this inverse. Okay. Now, when we have this, then we are going to have two structures, right? We have two structures. So we will be going to use the product rule. Okay. So first, we can write partial y. I will write xy. This becomes sine inverse xy plus, you see, y, and then over, the whole thing goes down, and 1 minus xy squared, and then chain rule, yx differentiate with respect to y, it's become x. Okay. Okay, I hope up till this product rule very clear what I've done here. So if we put 1.5, this will be equal to sine inverse half is pi over 6, right? Pi over 6. So pi over 6 plus this is half, this is half 1 over 4, and then 1 minus 1 over 4 is 3 over 4, right? So this will be half square root of 3. So this will be 1 over square root of 3. Okay, that's for number 38. Okay, now let's see if you can solve number 44. If you solve it, you can try your best to write in the chat, maybe using brackets and then divisions. Okay, for example, maybe if you write x divide x minus y, probably. Okay, try to write on the chat box. So you need to find two answer, dz dx and dz the y. Let's start from x first. From x. Anyone find the answer for dz dou x? And I think after this class, you can also check your other questions from here. I think I've sent you this attachment in the Moodle. If you check the Moodle, you can check the all the exercises. Okay, anyone got the answer? Or do you want me to work on? I hope implicit still doable for you. Okay, and y to square root. I think the bottom part a little bit wrong. The bottom part. I'm not sure why you still have the square root, but the top one is correct. It should be L and Y. Any other answers for dou z over dou x? Remember that the z squared, when you have implicit with respect to x or y, you treat the z as similar what you've done in the implicit in calculus 1 for dy over dx. So when you derive the z squared, it will goes by z squared becomes 2z, right? Becomes 2z dou z dou x. Yes, yes, yes. That's correct. Okay, that's correct. Okay, now if you look on, maybe I'll write here to make sure we can see from the top. So yz plus x and y equals z squared, right? So first we derive with respect to x. So x will be our variable, z will be our implicit, and y will be our constant. So this becomes y and dou z dou x, and this becomes just L and Y plus L and Y, and this becomes 2z dou z dou x, and we can put the 2z minus y equal L and Y, and then dou z dou x becomes L and Y, and then 2z minus y. Okay, now how about the if we use y? I think I will just do it for you. So we can take this, right? And because of this two is our functions, now we have a product rule, right? Product rule. So first is z plus y dou z dou y, right? And then plus ln y becomes 1 over y, so x over y. And then this will be 2z dou z dou y. So dou z dou y is equal, or let me group 2z minus y. Okay, and then this equal to z plus x over y, and dou z dou y z plus x over y divided by 2z minus y. You can write just like this. Okay, one more question. This is, yeah, the higher order derivative. So it has three derivatives. So third derivative with respect to y, x, and y. I think it's not too difficult, right? Should be, let me write here for you. F xy is sine 2x plus 5y. The question is asking partial y xy. So first we need to find the partial y. Partial y sine, and the function is inside, so it's become cos 2x plus 5y, and then multiply with 5, right? With 5. That's our partial y. And then partial yx is derive cosine become negative sine. So negative sine 2x plus 5y, and then we are using 2. 2 multiplied by 5, it's 10, right? And then we derive with respect to y. So we will have, this will be negative 550 cosine 2x plus 5y. Okay, I think not a problem at all. You just need to be careful when you're dealing with this partial derivative. Be careful when you see which variable you are going to derive with respect to x or with respect to y. Okay, that's you need to to be clear of. Okay. Okay, I think we can move on to next sections on the partial derivative, which is the chain rule. Okay. So since it's partial derivative, we have observed that we might have one path. We have more than one path to achieve our chain rule. Okay, because we have a partial parts, right? So if we remember the chain rule, in parametric, recall, okay, parametric, we have dy over dt, dy over dx, and then dx over dt, and we can use this chain rule to state that dy over dx is actually dy over dt divided dx over dt, right? If you remember the chapter 10. Oh, first question here. I think this solutions. The bottom part, this part is solution. The top part, this one is just proving the sine inverse x, derivative of sine inverse x. Okay. So basically, what you need to do is, because you are going to partially derive with respect to y, then this y here and the sine inverse, it also has y. We have two functions, right, with respect to y. So we are going to use the product rule. So this is the product rule. Y becomes 1. This is state as it is. The second part, this is sine inverse derive and then multiply with y. This becomes yx and over square root of 1 minus xy squared. Okay? Okay, any other questions? Okay, so far, if you are dealing with exercises like from this typical exercise, and I believe this will be helpful for you if you want to be more familiar with the partial derivative. I hope you can check some other questions as well. Okay, at least try the typical questions first. Okay, the typical question first. Okay, let's go back to the next page. The chain rule. Okay, so we have learned on the chapter 10, right? So we can state that if we have z and our z is a function of xy, if in parametric if we take back the parametric, if x is actually, we can say that x is actually function of t, okay, and y also function of t, then z expressed as a function of variable t. We can express z in terms of t. How we are going to do that? We are going to partially differentiate z using the chain rule, with the chain rule. So we can write z with respect to t now. So dou z dou t is dou z dou x and then dx dt plus dou z dou y and dy dt. So we will have a partial terms in our equations. Okay, this is just for an intro. Now the idea, okay, the idea behind it, the chain rule, we can set up a tree in the diagram. We can map the chain rule. Okay, we can map the chain rule. So start from z, and we know z is function of x and also y, function of two variables. And we know that x is function of t, y also a function of t from our definitions at the beginning here. Okay. Now to define all the paths that is possible in chain rule, we can write this dou z dou x, and the single variable will be dx over dt, and the other part will be dou z dou y and dz dt for single variable. So if we want to take z in terms of with respect to t, then we will get dz dou z dou x multiplied with dx dt. Similarly with the other one, dou z dou y multiplied with dz dt. So in more general terms, in general, we can write. So if you have more than 2, 3, 4, or maybe 7 variables, we can still do this chain rule. Okay, we can do this approach. So for example, if we have w is a function of x1 t, x2 t, x3 t, and so forth, then your derivative with respect to t, this will define by each element or each variable for y. So this plus and you can have more and more variable as well. Okay. Okay, now if we have example here, z is function of two variables, and x is also function of two variables uv, y also function of two variables uv. Now we can set up the tree. So if you're not familiar how to write directly, you can write in terms of the schematics tree. So z, x, y, and x having u and v, y having u and v. Now each part will have each possibility for each partial. So if we are going to have the chain rule for, let's say, z with respect to u or respect to v, for example, dou z dou u, this will be dou z dou x dou u, and then plus dou z dou y, and all will be a partials, and dou y dou u. If we want to have maybe let me resize this to make sure it can be right in here. So we have the other dv, we have dou z dou x dou v plus dou z dou y dou v. Okay, and in terms of writing, if you have branches like this, you write with Leibniz notations. Okay, but if you have just a single branch like x and t, we write with terms d, okay, dx dt. That's the differences, to make sure that we write the same or consistent symbols. Okay. Continue to write the notes. Okay. Uh, Let me check. Okay. Okay, let me move to the next page. Okay, let me just recall. Okay, recall. In calculus 1, if we have y cubed plus y squared minus 5y minus x squared plus 4 equals 0, if you are going to implicitly derive this, we can write this become 3y squared dy over dx plus 2y dy over dx, right? Minus 5 dy over dx minus 2x equals 0. And if we take this dy over dx, this will be resulting in 2x over all the 3y squared plus 2y minus 5. Okay, this is our dy over dx, right? Now actually, if we are using partial derivative, okay, if you're using partial derivative, so we can have like y cubed plus y squared minus 5y minus x squared plus 4 equals 0. Now, if we have y is actually a function of x in terms of our functions here, then we can set up that we have dou f dou x equal, right? So we can set up the functions. We have x, we have y. Okay. This is dou f dou x, and this is dou f dou y. But y is function of x, so we set up another 1x here. And this will have dy over dx. So we will have, from our tree diagram here, we will have dou f dou x plus dou f dou y dy dx, right? This will be equal to 0, and we can set up the general formulations. Dy over dx is equal negative df dou x divide dou f dou y, or we can set up this dy over dx as minus partial x partial y. Now, if we check the equation here, if we check the partial x, what is partial x? It's only this part, right? On the x, this is a to x. Partial y, 3y squared plus 2y minus 5. And it's perfectly partial x, partial y. And then take negative, it's become positive. Okay? Can you see how it relates to our partial relates to the calculus 1 implicit formulations? So we will have the formulation for dy over dx is minus partial x over partial y. Okay, any questions? Any questions? So you might have several methods to partially derive a function. You have the implicit. You can derive through partial directly. It depends on you, which way you are going to take on. So next Friday, we will start on a new section, which is we call the gradient vector and directional derivative. Okay. Any questions from this part? Anyone? If not, then we will move to the feedback time. Okay, I want to have feedback time, and I hope the time is sufficient for some of the questions. Okay, let me go to the QR code. Okay, so please scan if you haven't, and if you have scanned the QR code, we will play some games like usual to check our understanding. It's not that the question is a simple question. It's not too difficult. I hope everyone can join the game. Okay, let's start the game. Let's start the game. Okay, please check in the game. Okay, let me wait for 1 minute. Only 3 questions, and I hope the time enough for each question. Okay, let's start. Let's start. Get ready. And I hope you use your student ID. Okay, student ID. Okay, let's start. 3, 2, 1. Okay, I hope the time okay for you. Remember, finding the limit, aside from substitutions, you can check the path. Okay, check the path. Okay, it doesn't exist. You can check y equal x if you want, and check when y equals 0 or x equals 0, it will be a different answer. Okay, next part. Okay, next question, the second one. Okay. Okay, good, good. Okay, get ready. Second question. Okay. Okay, you need to write the answer. Not sure the time is enough. Hopefully it's enough. Okay, hopefully enough. Because it's a simple function. Be careful, okay, be careful. Be careful on when plug in the number. 15. Okay, 10, 9, 8, 7, 6, 5, 4, 3, okay. Okay. Correct answer is 1. Okay, good. Some of you are good, get the correct answer. Sorry if it's too short, the time too short. But I think it should be okay because it's not too complicated. Okay, still book. Okay. So which one of you are going to win the game? Okay, last question. Careful. Careful, read the question. Okay, hopefully the time is enough. Okay. And you need to write in terms of which ABC, okay, which ABC. So you need to write the tangent plane in terms of z equal to ax plus by plus c, and you need to find which one is ABC. Okay. I hope the time is okay for this case. Mm. I'm not sure what is happening now, but let me check. Okay. Oh yeah. Okay. 3 students got correct. Wait. Wait. Sorry. Okay. Okay. I think we finished. So congratulations for book win the game. Okay. Okay. Thank you for joining the game. So hopefully you can have beneficial from our lecture today. Yeah, Palace, congratulations. Okay.